Hello everyone. In continuation with the Thinking Machine series, I would like to introduce another point of view for building thinking machines. You should look at my earlier video series to get better context and continuity, which will help you get into learning groove. The core CGI hypothesis, a comprehensive theoretical framework aimed at understanding and ultimately building general intelligence, whether it be the intelligence we see in humans or the artificial general intelligence that is the aspiration of many in AI research. This hypothesis proposes that intelligence arises not from a single monolithic system, but from a continuous and synergistic interaction of two fundamental components. On one hand, we have cognitive synergy, which encompasses all the mechanisms for acquiring, representing, and processing knowledge. On the other, we have intentional dynamics, which provides the system with its goals, motivations, and direction. The core idea is that true general intelligence emerges from the constant feedback loop between these two, represented by the equation G equals C interacting with I. The first core component of the CGI hypothesis is cognitive synergy. Think of this as the knowledge engine of the intelligent system. It's the part responsible for taking in information from the world, organizing it, storing it for later use, and processing it to understand and predict. A key feature of this component is its approach to knowledge representation, which isn't limited to just one method. Instead, it advocates for a hybrid approach, combining the precision of symbolic representations with the robustness of subsymbolic or connectionist methods. This allows the system to handle both abstract concepts and noisy real-world data effectively. Underlying this is a suite of core cognitive processes, including memory for storing information, learning mechanisms to adapt and improve, reasoning abilities to draw inferences, and attention to focus limited resources on what's most important. Diving deeper into knowledge representation, the CGI hypothesis emphasizes the strengths of both symbolic and subsymbolic approaches. Symbolic representation uses explicit symbols and logical rules, allowing for clear and precise knowledge, ideal for tasks like logical deduction. On the other hand, subsymbolic representation, as seen in neural networks, uses patterns of activation to represent concepts, making it excellent for recognizing complex patterns in sensory data, even when that data is noisy or incomplete. The real power comes from integrating these two. Architectures like the atom space, which uses weighted and labeled hypergraphs, provide a common framework where symbols and subsymbolic patterns can coexist and interact, allowing for a more comprehensive and flexible understanding of the world. Operating on this rich knowledge base are the core cognitive processes. Memory is crucial for retaining past experiences and knowledge, whether it's factual information or learned skills. Learning allows the system to adapt to new situations and improve its performance over time through various methods. Reasoning enables the system to think logically, make predictions, and find explanations. Finally, attention mechanisms are vital for managing the overwhelming amount of information an intelligent agent might encounter. Concepts like economic attention allocation help the system to intelligently focus its limited computational resources on the most relevant aspects of a problem or situation. Moving on to the second fundamental component, intentional dynamics is what gives the intelligent system purpose and direction. It's not enough to just have the ability to think. There needs to be a reason why the system thinks and acts in a particular way. This is where goals, motivations, and emotions come into play. The CGI hypothesis proposes a hierarchical structure of goals, where broad, high-level objectives are broken down into smaller, more manageable sub-goals. Furthermore, motivations and emotions are seen not just as feelings, but as critical internal states that influence which goals the system prioritizes and how it allocates its cognitive resources. The goal hierarchy is a crucial aspect of intentional dynamics. At the top, we have broad, often long-term goals that reflect the fundamental drives of the system. For an AI, These might be programmed, such as to acquire knowledge or solve complex problems. To achieve these high-level goals, the system generates instrumental goals, which are more specific and actionable steps. This hierarchy is not fixed, it's dynamic. The system constantly evaluates the current situation, the progress towards its goals, and the emergence of new opportunities or threats, leading to adjustments in goal priorities and creation of new subgoals as needed. The true power of the CGI hypothesis lies in the continuous and bidirectional interaction between cognitive synergy and intentional dynamics. General intelligence isn't just about having a lot of knowledge or being able to process information quickly. It's about having a purpose that guides that processing. In this dynamic interplay, the goals set by the intentional dynamics component direct the focus and efforts of the cognitive synergy component. The outcomes of these cognitive processes, in turn, provide new information and feedback that can lead to the refinement, modification, or even the creation of new goals within the intentional dynamic system. This ongoing cycle is what allows an intelligent agent to be both purposeful in its actions and highly adaptive to a complex and ever-changing world. The core CGI hypothesis has significant implications for how we approach the development of artificial general intelligence. Rather than focusing on creating narrow AI systems that excel at specific tasks, the CGI framework offers a blueprint for building more general-purpose intelligences. It emphasizes the importance of not just developing sophisticated cognitive abilities, but also of equipping AI systems with a robust system of goals and motivations that can guide their actions and learning. Projects like OpenCog are direct attempt to implement these principles, integrating various AI algorithms within a common knowledge representation and driven by a goal-oriented attention allocation mechanism. This framework is not just a theoretical construct. It provides a valuable and actionable roadmap for future research and development in the ambitious pursuit of creating truly general artificial intelligence. I am now happy to take any questions and comments. I will further share the more insights and details about how to build thinking machines and underlying principles in my coming video series. Please subscribe my channel and like the video so that I can bring interesting insights and updates on thinking machines.